which you guys shouldn't have to worry about. Teenagers have logical reasoning skills I mean, it's coming out the wazoo, right? You guys are so logical with reasoning. Not a problem with you guys. So, here are some identities. Here's some of the ones you're going to have memorized. These are called the reciprocal, trigonometric identities. Those are pretty much. The reciprocal identities are the following. Sine of x is equal to 1 over the cosecant of x. Cosine of x is equal to 1 over the secant of x. Tangent of x is equal to 1 over cotangent of x. And I guess we should write these. The opposites of these are also true. If the sine of x is equal to 1 over cosecant, then what is cosecant of x equal to? 1 over the sine of x. Or the secant of x is equal to 1 over the cosine of x. And the cotangent of x is equal to 1 over the tangent. I know I'm writing pretty quick. Sorry. There's also these two, which really aren't reciprocal identities, so I'm going to call them something different. These are really called the ratio identities. Ratio identities. In your book, they call them the reciprocal identities, but really they're called ratio identities. You use these ones really often. The tangent of x is equal to sine of x over cosine of x. The tangent of x is equal to sine of x over cosine of x. You use this one quite a bit in this lesson in particular. Now, just an explanation of why the tangent of x is equal to sine of x over cosine of x. Think about the unit circle definitions. What was the definition of tangent on the unit circle?
Y over x.
Y over x.
Sine is y.
Sine is y, cosine is x. You see that? Yeah. So the other one is the cotangent. What's the definition of cotangent on the unit circle? X over y. So then the ratio identity would be cosine of x over sine of x. These two you use quite a bit. The reciprocal identities, not so much. Every now and again, but ratio identities, quite a bit. This one, though, you use all the time. The Pythagorean identities.
I'm pretty sure I'm liking this one.
Squared equals sine squared plus cosine squared.
Close. Really close.
Wow.
You guys know the Pythagorean Theorem, right? A squared plus b squared equals c squared. Well, think about the a and b as x and y. So x squared plus y squared equals... On a unit circle, what's the radius of a unit circle? The radius is half the diameter, but on a unit circle the radius is 1. So on a unit circle, just let me draw this unit circle real quick. If I chose a point on the unit circle and drew a right triangle, isn't that x and that's y? But what's the definition of x? Cosine, what's the definition of y? Sine, and that radius is equal to 1. So instead of x squared plus y squared equals 1 squared, how can we change this into a trigonometric identity? Sine squared plus cosine squared equals 1 squared, which is just 1. So that's the Pythagorean identity. Sine squared of x plus cosine squared of x is equal to 1.
So the square comes before the x.
Yeah. Now there are various variations, that's an oxymoron. there are variations of the Pythagorean identity, which you must also know. What would happen if I... Take a look up at the screen for a second. What would happen if I divided each of these terms by sine squared of x? This doesn't really disappear. It becomes 1. So this is 1 plus... What's cosine over sine? It wasn't tangent, it was cotangent. So this is cotangent squared of x. And what's 1 over sine squared? So this is cosecant squared of x. This is another variation of the Pythagorean identities that you need to know. 1 plus cotangent squared is equal to cosecant squared. Now you guys, here's the deal. Yeah, if you have a good memory, this might come a little bit easier for you. If you don't, you need to understand where this even came from. Rather than just memorizing it straight up, where did this identity come from? It really came from the first one. How? Dividing everything by the sine. Okay? Well, there's another variation. How do you think we're going to get that third variation? Dividing everything by cosine. And that's what I'm going to try to do when I present these identities, is show you where they came from, so you might have a better chance of remembering them. But if we divided everything by cosine squared of x, then what is that? What's the third variation? Yeah, sine over cosine is tangent. So that becomes tangent squared of x plus 1 is equal to secant squared of x. Those are the 3 variations of the Pythagorean identity. Well, that's actually not true. Sorry. I want you to draw 2 lines coming from this identity. Isn't this also true? How did I get that? Just subtracted the cosine squared. Or isn't this also true? So, just different variations of the Pythagorean identities that you will be using from time to time. Here's an actual example of what an identity is. An identity... an identity. An identity means proving that one side of an equation actually does equal the other side. That doesn't mean that you solve the equation. Here's what I mean. It's kind of like proofs. Here's an identity. Cosine of x over secant of x sine of x equals cosecant of x minus sine of x. This is what's called an identity. We don't have to solve this equation. We're not solving for x. That comes later on in the chapter. What we have to prove is that the left side really is equal to the right side. Alright?
Awesome.
We have to prove that one side is equal to the other. We can either go from left to right or from right to left. It doesn't matter. Okay? Now, the one important thing is, and you guys need to understand, there are certain guidelines and big no-nos. Okay? First guideline is you choose a side and you work only with that side. It doesn't matter if it's the right or left, but you choose a side. Here's guidelines. Choose a side and use only that side. You're not performing operations to both sides. Like, you're not going to add 1 to both sides or divide both sides by 10 or whatever that is. That's solving equations. We're not solving equations. We're doing a proof. You all understand that? You can't perform operations to both sides of this. Generally, you're going to want to choose the more complicated side. That's usually going to be your best bet. Not always, but usually. You're going to choose the more complicated side. So considering the two, which one would we maybe consider? And sometimes it's not an easy distinction, but between the two sides, which one seems more complicated? The left side, that's what I would say, maybe the left side. So we're going to choose the left side and use only the left side. Once you've chosen a side, you use known identities. Not identities that you make up, but use known identities to change the side you've chosen use known identities to change the side you've chosen to look like the other side. You guys have to be patient with this. Okay? I'm going to explain something to you here. Many of you, not all of you, but many of you have had an easy time in math. Math comes easy for a lot of you, and that's great. You're in an honors course, that's wonderful. And this always doesn't come easy to everybody. That doesn't mean you're dumb. It doesn't mean that you don't get things. It just means this is a different kind of math. This is not just simply performing arithmetic operations and simplifying things and following an algorithm. Algorithms are easy to follow because it's step 1, step 2, step 3, step 4. Okay? This is your own creativity. This is your own. You're all on your own. You have to be patient. It gets easier. Okay? It gets easier with practice. But if your attitude is, well, I don't understand it within the first 5 seconds, I'm not going to try it, you're never going to get anywhere. Okay? Quite often, you're going to have to start a problem, you're going to get stuck, you're going to have to erase everything and start it again. Or you may have chosen the wrong side. Maybe you start with the other side. You're going to have to be patient. These problems don't come easy sometimes. Okay? I'm just telling you, especially with students of your caliber where things generally come easy to you, when you get to a point where things don't, you think, oh, the whole world's falling apart. It's not. Okay? Save your tears and just grit your teeth, squeeze your butt cheeks, and get through it. Okay? So, we have chosen the left side. Cosine of x over secant of x, sine of x. Actually, no. We're gonna save this one. I want to start easier. Sorry. Let's do example. I want to start easier.
I'm trying my best.
I thought we were sticking aside. Sticking to it.
No, I don't want to scare you guys away. Let's do this one. This one's easier. Cotangent, secant over cosecant is equal to what? Let's try this one. This one is easier. First of all, it's easier to spot the more complicated side. Right?
One.
That's the right side.
Let's choose one. Let's make one.
Definitely the right side.
So I would safely say that this is the more complicated side.
But what if you could, if you choose one, you could probably, like, it might be really easy if you just plug it forward with this.
You can try it that way. But let's assume that we're all agreed that the left side here is a little more complicated. So cotangent, secant over cosecant. Somehow we've got to simplify, use identities to prove that that is equal to 1. Now, it's really helpful to think ahead. Since we have a fraction, you guys listen to this, since we have a fraction over here, and that's eventually supposed to equal 1, when is a fraction ever going to equal 1? When the top and bottom are the same. So it helps on these problems if you have kind of a plan or a direction of where it is you want to go. Because we know this is supposed to equal 1, we should probably try to get the same type of expression in the numerator and the denominator, because that means we're going to have a fraction that equals 1. So all we can do is use identities. We can't add things to both sides. We can't subtract or anything like that. We have to only use identities. So here we go. Use some identities. Now, do you see anything that's being squared? There's nothing that's being squared. So that precludes the what kind of identities? Or excludes. We're not going to use Pythagorean identities. That really only means we can use the reciprocal or the ratio identities. What do you think?
If you switch the cosecant and secant, since like they're equal to their opposite over 1, so if you switch their places and turn them into sine and cosine, would that be okay?
Okay, let's show all the steps though. So you're saying that the cotangent, or you're saying the secant is 1 over the cosine, and this is 1 over. Is this what you're saying?
Can you just move it down?
Yeah, make it so the sine on top and cosine x on bottom.
Now you could. I just don't want to skip all the steps ahead. Now we can write this as cotangent times the sine. No, let me slow down here. Do you understand what happened here?
No.
Not really. Kind of.
Well, where did this? Let's start even slower. Where did this come from? Right here, 1 over the cosine. That's reciprocal. And then the 1 over the sine is the reciprocal of cosecant. So that's where these two came from. But then how did we go from this to that?
You just switch them? Why would
So that would be over 1.
why would you not just switch them?
You'll see in a second why we wanted to. This is actually a pretty good direction to head. But how did this go from here to here? Well, consider the whole entire numerator and the whole entire denominator. Dividing by a fraction is the same as multiplying by the reciprocal. You guys follow? This expression is being divided by that expression. Dividing by a fraction is the same as multiplying by the reciprocal. The reciprocal of 1 over sine is just sine. So I multiplied by sine over here. Multiplying by a fraction is the same as dividing by its reciprocal. So we could have divided this by its reciprocal, which is cosine. This is just some clever manipulations that have to happen. And why did we want to do that? This doesn't seem any less complicated than what we started with. Go ahead right here.
And why do we only do those two? Why not do the
We could have, but it would have been best not to. You're right. We could have done the reciprocal of the cotangent. Let's go here.
No, wait, sorry, tangent of x equals sine x over cosine.
Oh, so
That's not what you
tangent
want.
of x
That would be tangent of x.
So could you do
Yes, but you want to plug the cosine.
Does tan of x times tangent of x equal 1?
I don't know.
Yes, you do.
It's there.
Well, I'm asking you guys. Does it? Here's this right here.
Figured it out.
What is sine over cosine, you guys?
Tangent.
The sine over cosine is tangent. So couldn't we turn this into
Tan times.
cotangent of x times the tangent of x?
Which is 1. Because of the reciprocal.
And what is the tangent of x? 1 over the cotangent, right? Isn't the tangent equal to 1 over cotangent? So now you could change this into the cotangent times 1 over the cotangent of x. And what does that equal? Now here's the thing, and it's often the frustrating thing about identities. This isn't the only way this could have been done. This isn't the right way it could have been done. There are other ways it could have been done.
Wait, is it the right way? But it is the right way.
I mean, it is one right way. It's not the right way. Did anybody maybe think of another way to have done this? Jake, what do you think?
You could have plugged in for cotangent the cosine of x over the sine of x and then they cancel out.
So let's go back up here and do a spin-off. You're talking about this cotangent here?
Yeah.
So change this into what?
Cosine of x over sine of x.
Cosine of x over sine of x times the sine of x over cosine of x. And then what would have happened? That would have equaled 1. So there's another way that could have been done. So that's...
Couldn't you already simplify secant over cosecant?
What's the identity for secant over cosecant? We don't really have one for secant over cosecant. We eventually did, but we had to do some other identities first. So it's a good and a bad thing. It's a good thing that there are multiple ways, but it's also kind of a bad thing that there are multiple ways. It could be a little frustrating. But this is what an identity is. Do you see how we chose only the left side and we changed that left side to make it look like the right side? You see how that worked?
Yes.
Let's try another one. These will just get progressively more sophisticated. Example 2.
That's another way to say
No, harder.
harder.
Possibly.
Did you say for sophisticated?
Life will never be easy.
Sine of x plus cosine of x in parentheses to the second power is equal to 1 plus 2 sine of x cosine of x. Other than the obvious that these are super fun to do, the other reason that we learn these, when you guys next year get into calculus and you have to start doing derivatives and integrals, sometimes it's a lot easier to take the integral of, for example, this than it would be to take the integral of this. Aren't these equal to each other? It's much more difficult to take the integral of this than it is to take the integral of that. So if you are faced with a problem in calculus where you have to take the integral of something that's very difficult, you can use the identities to change it into something easier, and then the integral becomes easier. Does that make sense? So this is very useful for next year. We're kind of laying the groundwork for a successful AP calculus year. But which side here might look more complicated? We're going to choose the left side again? So let's choose this side. So sine of x plus cosine of x to the second power. Somehow, well, this one actually isn't so bad. Somehow we're going to have to change this into the right side. Let me ask you this question, you guys. Couldn't we just distribute the exponent to both of them? No. That's algebra 2 mistakes. You can FOIL this using the FOIL method, sine plus cosine times another sine plus cosine. Sine of x plus cosine of x plus another sine of x plus the cosine of x. If you use the FOIL method, this becomes sine squared of x plus 2 sine of x cosine of x plus cosine squared of x. And maybe now you'll see that this one isn't so bad. Let's let it catch up.
You just need to make sine square the way it is. Okay, yeah, that's easy.
Don't yell it out. Let people think and stew over this for a second. If you've got it, write it down. If you think you've got it, write it down. Aren't we pretty close right here? We have a 2 sine x cosine x, which is what we need to have, but where the heck does that, don't answer out loud, but where the heck is this 1 going to come from right here? There's no 1 down here, but there is an identity that we can use. You could, you certainly could. Look at this and look at that.
You divide them?
Yeah, you could. You could, but there's an easier way. What is sine squared plus cosine squared?
1.
How do we know that? That's the Pythagorean identity. Sine squared of x plus cosine squared of x is equal to 1. So this equals 1 plus 2 sine of x cosine of x. Double check that against what we've, isn't that what we wanted to show? Okay. Let's do example 3 here. This will have to be our ending point. We're going to have to pick this up next time. Secant of t minus cosine of t over
Why is T on that?
the secant of t is equal to sine squared of t.
Well, now I'm thinking the right side.
Well, we could manipulate it so that they eventually could. Here, so let me actually kind of talk about what you were saying, because can I just go like this? The secant's connected to the cosine. However, what about this? So, is it safe to say that we're going to choose the left side as our okay. So, secant of t minus cosine of t over secant of t. Are these equal to each other? Are those equal to each other? What did I do there?
I kind of just separated the one fraction. I separated this one fraction into two. Now just double check though, if this one on the right, if I combined that back into one fraction, would it equal the original one? It would.
So that'd be 1 minus.
So now we can cross out the secant.
Well, they don't really just disappear. Secant divided by secant is 1, so this equals 1 minus cosine of t over secant of t. Ooh, we're getting there. Parker, go ahead.
So would you always choose the more complicated side?
95% of the time, yeah. 95% of the time.
Can you give us a problem when you wouldn't?
Not today. Oh, we only have 1 minute. Shoot. Okay.
Don't fail us.
Here's something I want you guys to ask, or to ask yourselves. Sine squared of t. Eventually, we're going to have to make that. What is the sine squared equal to? 1 minus cosine squared. So that's the direction we're going to have to head. Bell hasn't rung. Why are you putting stuff away? So how can we change this into 1 minus cosine squared? That's what we need to do. Go ahead, Gentry.
Secant equals 1 over cosine of x.
Good. So let's change this into 1 minus cosine of t divided by 1. Oh, is that what you're talking about?
And that gives you
Cosine divided by 1 over cosine means times cosine. So that changes into 1 minus cosine squared. And what is 1 minus cosine squared?
1 minus cosine equals sine squared.
That's equal to sine squared. Is that, did we finish?
Yes.
Woo, we finished. All right.
Why does that, how do you get it? Why does that make it cosine squared? Like, why does it
Why does what equal what?
So why is it cosine
If you go back to Pythagorean identities, if you subtract the cosine on both sides, then it becomes sine squared.
I can tell you my joke, okay?